Hi, I am Eber Wanger-Kolesi, and today I will be presenting our paper on the risks of collecting multidimensional data under local differential privacy, which is accepted at the VLDB 2023 and was done in collaboration with Sébastien Gams, Jean-François Couchou, and Katusha Palamidesi. So to start with some introduction, I'll talk about the good side about privacy attacks, as this is a driving motivation since privacy attacks play an essential role by complementing the mathematical or theoretical work on privacy research. It also allows to identify vulnerabilities as well as to interpret the privacy claims. For example, when they identify the failures of pseudonymization and evented key anonymity through identification attacks, or also to reconstruction attacks that inspired and adopted the adoption of differential privacy. So we'll be talking about the local differential privacy, which is the decentralized setting of differential privacy. So in this case, the definition is more about any two input values v and v prime that the user may have in the domain of the mechanism, and any output z in the range of this mechanism. So we need to satisfy local differential privacy. The ratio between these two probability distributions should be bounded by E to epsilon. And epsilon is an important parameter as it computes the privacy utility trade-off. So some fundamental differential privacy properties in general is that it's robust to post-processing. So we can apply any function on the result of differential privacy mechanism and we cannot break this guarantee. And we can also compose many differentially private mechanisms such that we can compute the overall privacy loss that we are incurring. So what is driving us for the problem statement and assumptions, here is a tiny example that considers a server that aims to collect the multidimensional data about the population, and the server wants to survey this population multiple times because it always sells this information to third parties and offer discount and the statistics for the user, so the user can opt in or out of a given survey. So the server assumption is that it knows the user's pseudonymized IDs. It also has no knowledge about the real distribution. That's what the server wants to estimate. But it may have some access to background knowledge, for example, census statistics. And to do the LDP part, it uses state-of-the-art solutions that I will present in the next slide. So one of them is called random sampling, in which the user has a tuple of one value per attribute, and it randomly selects a single attribute and allocates the whole privacy budget to it. So in this case, the user says which attribute was sampled and the locally differentially private value. So our insight to attack this later is that all the privacy budget is being allocated to a single attribute. So another state-of-the-art solution is called random sampling plus fake data. The idea is the same. The user has a tuple of values. It samples at random a single value and uses a locally differentially private value. So for all the non-sampled attributes, it will also generate some fake data following the uniform distribution. So in the end, the server will not know what is the sampled attribute because it will see a whole tuple of sanitized values, and what are fake data, it doesn't know. So our insight here is that the fake data follow always a uniform noise, so we'll show later that we can attack this. So a summary of our contribution is that we propose distinguishability attack, in which, for example, the sampling solution always uses the whole privacy budget to a single attribute, so we call it value distinguishability, in which the user has a value v, apply a local differential privacy mechanism to generate z, and the server looking only at z, it can predict back the value of this user. We also present a fake data distinguishability, in which for the random sampling plus fake data solution, the attacker can distinguish what is the fake value of the LDP value. So we can uncover the sampled attributes. So we can come back from the random sampling plus fake data solution to the sampling solution. So this will be vulnerable to value distinguishability as well. And we show that in multiple collections over time, the adversary will also be able to profile the users by using distinguishability attack, and by using some background knowledge, this can lead to some identification risks. So now, after this introduction, I will enter more in detail about the attack-based approach to local differential privacy, starting with value distinguishability. So here the case is that each user has a value v from an attribute, from discrete attribute of size k. The LDP mechanism is using the sampling solution, And the goal of the adversary is to predict the user's original value v by looking only at z and with knowledge of the mechanism. The metric we will be measuring is the accuracy, and the baseline here would be just a uniform random guess about the domain size of the user. So here is an example of a state-of-the-art LDP mechanism, which is called the generalized randomized response. So in this mechanism there is no encoding, so the user will report their original value with some probability p parameterized on epsilon. Otherwise, it will report a totally random value except the original value with some given probability. So we can see the probability p as the probability of being honest, while when another value is reported is the probability of randomizing. So the good thing about this mechanism is that by seeing only z, we are not certain about the secret v of the user. So this provides us some form of a plausible deniability, in which we can define as if the v is an embarrassing value, as long as the probability p of reporting it honestly is smaller, the user can deny to have it. So our attack is based on this insight, because for any value we see from the user, we can assume it was reported honestly, because the probability p is always higher than q. So here is an instance of the value distinguishability attack results, in which we measure, for example, on the x-axis means privacy, the epsilon local differential privacy guarantee, and the smallest, the epsilon, the more private. And on the y-axis we have the attacker's accuracy, so the smallest, the best. And we can see that for many local differential privacy mechanisms, they have different attackability for the same level of epsilon local differential privacy guarantee. So now I will present the identification attack. Here the assumption is that the server collects multidimensional data multiple times. We start using the SMP solution, and the goal of the adversary is to profile and identify the user given 1 to 10 guesses. So our metric here is just the identification accuracy, if we identify or not the user correctly. And the uniform random guess in this case would be the top k divided by the number of users that we are collecting. So the attack model here is that we assume the adversary has knowledge to some side information, to background knowledge. We will be using a matching algorithm R, in which for the inferred profile Y that we profile the user through many data collections, we will match this profile and compute the distance with every profile we have in our background knowledge, and we will output a score vector C. Next, we will have a decision algorithm that will output a list of at most top k users that we have in the background knowledge that we inferred as the user's identifier. So here is a result of the identification results using the SMP solution. We average our results over 20 runs, and in this case we are using the GRR mechanism that I presented previously, and we varied the number of collection to 1 to 5. So we are presenting here the results also for epsilon on the x-axis. On the y-axis means the attacker's identification accuracy. The plot on the left is the top 1 identification, in which with a single guess we already identified the user, and on the right we have 10 guesses in which the adversary is given 10 guesses to identify the user. So we can see that with 5 surveys the identification rate will be increasing from the baseline guess to 10%, so we have a 10% increase, and if we assume the top 10 identification, we will have given a 30% increase over a random guess attack for the identification. So now I'll present the fake data distinguishability attack. We assume here the user has also a multidimensional data, but now it's using the random sampling plus fake data solution. And the adversary's goal is to predict what is the sampled attribute looking only at the reported tuple C. So here the metric, we call it attribute inference accuracy, as we aim to infer what is the sampled attribute, and the uniform random guess would be 1 divided by the number of attributes T. So in this case we have proposed many attack models, but I will be presenting one which we assume the more realistic, which is the no-knowledge model, in which the server has not compromised any users, it doesn't know any information about the sampled attributes of the users. So the idea is that After collecting the random sampling plus fake data, and by knowing which is the random sampling plus fake data mechanism and the epsilon guarantee used by the users, the server can estimate the distributions for each attribute, which is the goal of this random sampling plus fake data solution. So by estimating the distribution, it can also generate a fake data, a synthetic dataset, in which it can reapply the random sampling plus fake data solution by storing what was the sampled attribute. So this would be using a supervised learning classifier to train this classifier, and next to use this learned classifier to predict the sampled attribute of each user. So here is also an instance of the results, also averaged by 20 rounds. We have used here the random sampling plus fake data with the GRR mechanism, and we varied the number of synthetic profiles that the server wants to train. And we varied by 1n, 3, and 5 times the number of samples in the original dataset. So in this case, we have on the x-axis the epsilon guarantee, and on the y-axis we have the attacker's accuracy. So we can see that from the baseline to our attack, we can increase by 20% of accuracy by inferring the sampled attribute of the users. So if we continue to do this in multiple data collections, we could also try to see the risks of identification of the random sampling plus fake data solution. Here we also present an instance of this result for 20 rounds and with the GRR mechanism by varying the number of servers from 1 to 5. So we can see that now with the random sampling plus fake data solution, the risks here is not anymore 10% or 30% for the top 10. It's just a small increment in comparison with a random baseline. So now I will present a countermeasure solution. By knowing that random sampling plus fake data was already a natural countermeasure to identification attacks, because there are chained errors when we make the fake data distinguishability. We saw the accuracy is not 100%, and also on value data distinguishability, in which we cannot be sure that we inferred correctly the user's value. So in this case, what we did was, if the random sampling plus fake data solution is vulnerable to fake data distinguishability because the fake data follow uniform noise, we can try to generate a more realistic fake data. So that's why we call it random sampling plus realistic fake data, in which the fake data will be sampling from a previous year census or some domain knowledge that the users can use to generate this fake data. So here is an example of the results of the attacking the solution now with the same setting as before. And we can see that now the attack is much closer to the baseline, and we don't have this 20% increment anymore. So to conclude this work, we have identified new privacy threats for local differential privacy mechanisms following the random sampling and random sampling plus fake data. And we call it distinguishability and identification attacks, distinguishability for the value and for fake data. We also concluded that random sampling plus fake data is a natural countermeasure against identification attacks because there are chained errors that we have on the previous attacks. And we proposed an enhanced solution for random sampling plus realistic fake data, which can countermeasure against the fake data distinguishability attack. So as perspectives, we aim to use these privacy attacks for auditing differential privacy guarantees of these LDP mechanisms. We can also think of extending these attacks to more complex LDP mechanisms, as well as to infer the privacy risks of local deep privacy mechanisms, in which we have a notion of distance, and it's not pure LDP, but it's a different notion of local privacy, as well as to design a new countermeasure solutions not based on random sampling plus fake data. So thank you very much, and if you have any question, you can get in contact and I will be happy to answer.